Okay, hello everyone. Good afternoon. I'm going to introduce this paper, Optimal Transport Enhanced Cross-City Site Recommendation, and I'm the presenter, Xinhang. I'm from Tsinghua University, and also this work is supported by the City University of Hong Kong. So before introducing the methodology of this paper, I prefer to start with a preliminary knowledge of it. So to make sure that you understand which task we are going to do and some related techniques we use in this paper. So the site recommendation is a task that aims to recommend the optimal locations to open branch stores for a given brand by considering the existing branch stores. So the task formulation is similar to top K recommendations, where the brands in such recommendation actually stand for the users and the regions stand for the items. And as you can see, we have data like the example figure. We have some general features, which are the IDs, the names of the branch store and the cities. And also we have some commercial features like the categories, the brand, and some competitive or related brands. Also, we also have the geographical features, which are the longitude, latitude, and also some regions, nearby regions, similar regions, like that. The site recommendation is quite different from the top K recommendation is that the data sparsity is extremely high in site recommendation. That for in this data set, each brand only have 5 sites on average. So we came to understand that site recommendation on our target city may benefit from the information from other cities. So that's why we are doing the cross-city site recommendations. And so for this data set, we have these 4 cities, which are the Chicago, New York City, Singapore, and Tokyo. So question is that problem is really complex, but it's important to model the consumption habits or the lifestyles of residents in different cities. And we could see that each city actually have different lifestyles from all the other cities. So another thing is the optimal transport, which is the techniques we used in this paper. So optimal transport is a math theory or a computation method which aims to find the optimal transport plan with 2 different distributions. So it's actually to map the 2 distributions on it. A formula of the optimal transport can be that given to data distributions X and Y, the optimal transport plan T aims to minimize the overall cost by these formulas, where C is actually the cost matrix. So it's actually an optimal problem. So the key point of optimal transport is that the cost definitions. Should we use the Euclidean distance or the Manhattan distance? But in this paper, we prefer that to use the Gromov-Westerson distance. It's a special distance that is the distance of distances, which we will introduce it later. So it came to our methodologies. Our OTC framework, which is a proposed framework, consists of 4 parts. The first part is a single city model training that we aim to conduct the cross-city site recommendation, but before we need a single city model. So we can train the single city models separately for each cities. And then we will do a brand or the region projections to get the cross-city informations. And then based on the projected informations, we do the inference with these projected embeddings. And finally, overall, we have all the cross-city informations. We can do the cross-city recommendations based on it. So for the single city model training, it's just a backbone model training. So no matter what we use, it's just the backbone. We can replace the backbone with any other recommendation models. It maybe consists of 4 parts. The first, from bottom to highest, is the embedding layer, where we use the ID embedding lookup table as the embedding layer here. And for the interaction layer, it may be identity mapping or graph neural network. It may be corresponding to which backbone you choose to use. And the prediction layer is also according to which backbone model you use. And finally, for the ranking loss, the pairwise ranking loss, we use the BPR loss here. And then the second part is actually the most important one. That's we do the brand or region projections to make the information from the source city to the target cities. Here we use the Gromov weather scene-oriented optimal transport problem. As the formula shows, it's actually a distance between two distributions, and then we can obtain the optimal transport plan by solving this optimal transport problem, which we use the Xinhang algorithm here. And the distance between two embeddings in one distribution is defined as Euclidean distance. So after solving this optimal transport problem, we get the optimal transport plan for the brand projection and also the region projection separately. And we do the brand projection and the region projection also. With the projected informations, we can do the inference recommendation with them. That is when we projected these the brands or the regions from the source city to the target city, we can also get an inference recommendation result as or using these projected embeddings, which is shown as this formula. And then when we have already have multiple cross-city informations, we can get the overall recommendation results, which is the cross-city recommendation result. It's actually the single-city recommendation result plus the cross-city inference recommendation results. And also they are weighted summed by the weight parameters. So let's review the whole pipeline of this process. Is that we first do the single city training to obtain the single city model separately, and then we use the optimal transport algorithm to get the optimal transport plan. And then with this optimal transport plan, we can project the brands and also the regions. And with the projected brands and the regions, we get the inference recommendations. And the overall cross-city recommendation result is the single city recommendation result plus the inference recommendation result. So that's the whole pipeline of our proposed method. So then we turn to the experimental part. Here is the data set we use, is the OpenSetRec. Oh yeah, it's also the fourth presentation later. And we could see in this data set, we have 4 cities: Chicago, New York City, Singapore, and Tokyo. And they have different numbers of brands, regions, and sets. And also the lifestyles of the people in this city are quite different. So we need to model these cross-city informations. For the baseline models, we choose different type of baseline models. And also, since our OTC framework is a pluggable component, so we also choose the GWCDR as the framework as the most important baseline. So actually, it's no matter what backbone model you use, you can just use our OTC as an additional component to further improve your performance. And for the implementation part, we split the data with 70%, 10%, 20%, and the experiments are done on the V100 GPU. And for conducting the optimal transport problem, we use the POT library, which is open source. For the main results, we can see that our framework can remarkably improve the performance of the backbone models, both for the MF and light GCN. So it may be not so much, but considering that our framework is a lightweighted and also a pluggable component, it can be utilized to any backbone models, which means you have already got advanced backbone models with a higher performance, but you can still use this framework to further improve it. So for the ablation studies on different cities, we test the improvements brought by the source city to the target cities. And it's also an interesting finding that different cities will have benefit most from different cities. That Tokyo will benefit most from the Singapore, but least from New York cities. And actually, these four cities will formulate like a chain. So it's really interesting, but it's hard to explain why of this. And also, we have conducted the parameter analysis. We test the parameters for the source cities to the target cities. And it actually turns out to suitable weight parameters are very necessary for get remarkable improvements. Otherwise, you will even harm your original performance of it. And for the efficiency analysis, we could see that additional time cost of our OTC framework brought to the backbone models are marginal, which means you will only need a little bit additional time. You can get further improvements on your backbone models. Finally, one is this case studies. We choose several target city brands in New York City and some corresponding source city brands in Tokyo. And it's also interesting that the same brands are not exactly aligned, that the brands are different status in different cities. For example, the Five Guys, which is a fast food in New York City, but it actually, its corresponding brands in Tokyo are actually the alcoholic or the beverage shops. So it's really interesting that it didn't correspond to also the fast food brands in Tokyo. And also for the Lululemon, which is a sports brand in New York City, its corresponding brands are the fast fashions. So that's all our findings and also this work for it. Thank you very much. Thanks for listening.